If we could have his slides up. So, he's going to talk about IP over DWDM. It's a good talk, I've seen it before. Welcome.
Yeah, thanks for coming. So it's pretty complementary to what Byron just said. So I will give you a little more insight into IP over WDM. It's a strong trend, but what is it about? So I will start with, let's say, the definition of what we understand when we talk about IP over WDM, and then why it's a strong trend. So it's not new actually, but the thing is, with 100 gigabit technology, there was no colored optics, as Byron also just pointed out, that was able to go, let's say, over longer distances in an efficient way without sophisticated amplifier technology and, let's say, pluggable optics in a form factor that wasn't well accepted in data center and, this kind of environments and switches and routers. So there are some challenges with IP over DWDM with the latest technologies, especially going to 400 gig, which I'm going to talk about, and then our experience with customers and technology so far, and some practical examples. So IP over DWDM. Actually, when Smart Optics has been founded, the idea of founding the company was to take advantage of pluggable optics in host equipment and make it easy to build DWDM networks or CWDM networks at the time, like 18 years ago, for enterprise customers, data center customers, and that type of, let's say, applications. At that time, not focusing on the carrier market, more on the enterprise market. But what is?
Matthias,
yeah.
The screen.
Yes, thank you. So what is IP over DWDM? First, it's the animation doesn't work, right? Use, let's say, gray optics in a router connecting to a muxponder or transponder, as Byron has also just pointed out, and convert into a DWDM signal. And these were typically fixed lasers on the transponder or muxponder, or CFP2 or CFP4 modules that are interconnecting with the DWDM layer of the network. So that could be done with 10 gig, 100 gig, 400 gig, multiple 100 gigs. So that's why we have these flavors of transponders and muxponders. However, with that technology, I mean, there's a lot of overhead in equipment that is not necessarily needed if you don't need these transponders and muxponders for demarcation or for, let's say, more efficiency and traffic aggregation. So the idea of today's network is to just plug the coherent, tunable DWDM optic straight into the router and take advantage of the technology and save complexity in the network and these kind of things. So with today's technology, it's, let's say, possible to just use an open line system vendor for the DWDM network for multiplexing, amplifying, and let's say, routing the waves. With a pluggable DWDM transceiver that sits directly into a switch or a router. And I mean, why is it so attractive? One thing is, of course, cost savings. And the second thing right now is also lower power consumption. So power in data centers and cooling in data centers is actually a big problem with the high density of, let's say, heat dissipating components today, servers, routers, DWDM equipment, all consume a lot of power. And together with that, it's also less space, it's lower latency, because with the less OEO, so optical conversion we do, the less latency we have. And it also goes in line with lower complexity of actually building the network. And what allows all this is especially for the higher data rates now, is the introduction of these 400 gig ZR and ZR plus pluggables in the QSFP-DD form factor, which are very common in data center switches and routers that everybody's using today. So CFPs and CFP2s were there before, but not common in data center equipment. And another thing which goes in line with, let's say, this trend is in the past, the DWDM networks have mainly been designed around telco requirements for long-haul networks, for national backbones, for metro backbones, where service providers were actually making the connections for enterprises, for data centers, for cloud providers, interconnecting, let's say, the data centers, the metros, and the world. These days, most of the traffic is actually driven by the cloud providers, by the data centers, by large enterprises, and content providers. So many of these data center providers and cloud providers have started building their own DWDM networks. So they are leasing their own fibers, or they are even laying their own cables. And they are now taking advantage of, let's say, building leaner DWDM networks for their own use. So that's what we're seeing right now. And with these standards, I mean, there are also coming some challenges. So one is 400 gig ZR is an ORF standard, which has been developed more or less for data center interconnect. So it's well-defined in all aspects with regards to distance, optical power levels, interfaces, and so on. So it works perfectly for distances up to 120 kilometer in the metro to interconnect data centers. Power budget is a bit limited. 11 dB doesn't allow you to go that far. So you might still need amplifiers, but it's a robust and very performing technology. 400 gig ZR Plus is not really a standard, but it's an MSA that many vendors support. And it goes a little bit beyond 400 gig ZR, so it defines electrical interface and transmission standards that can be used, again, in a QSFP-DD form factor in a switch or router. And the complexity there is there's an open Setup Plus standard, an open ROADM standard, and some, let's say, vendor-specific standards like OpenXR. All together have the same idea in mind, bring this, let's say, sophisticated technology into a transceiver and make networks more, let's say, performing and more, providing more bandwidth. Here, I just pointed out one point. There are so many different CMIS versions. So CMIN is a Common Management Interface Standard for QSFP-DDs. And in order to support these complex tunable optics in a host, switch, or router requires actually firmware support in those devices. So in the early days of DWDM, it was pretty easy to use a 10 gig DWDM pluggable in any type of switch or router, and it just worked. With the QSFP28s, it got a bit more complicated. With QSFP-DDs, it's even more complicated. So the QSFP-DDs are almost a transponder in a pluggable. So it's a complete optical subsystem that has a lot of functions these days that are required to be supported in the software of the host. So innovations around coherent pluggable optics that are just happening right now. The first two generations of optics, so coming back to 400 ZR and ZR Plus, had a little, let's say, drawback, which was the low output power. So they were good in amplified point-to-point networks or in networks that were designed to support these optics. Recently, we got the high power of 400 gig ZR Plus to market, which comes out with 0 dBm output power. So that's way better to be supported in existing DWDM backbones with, let's say, ROADM networks, ROADM-based networks that were designed to take CFP, CFP2 signals, or 10 gig signals that came out at around 0 dBm power level. So that's pretty good. These also have a 200 gig 16 QAM mode that I come to in a minute, supporting 50 gigahertz grid networks. So otherwise 400 gig will require 100 gigahertz. Yeah, I do. So the next thing we are seeing now is open ROADM pluggables. Those are not yet there, but coming almost every month. So they are adding layer 1 encryption, and they are also adding in-band management capabilities and OTN support. So those will take this, let's say, embedded approach to the next level. And yeah, with enhanced DSP technology, there will be also, let's say, new modulation formats coming up, like probabilistic shaping to optimize a modulated signal for certain applications, subcarrier technology, so transmitting multiple carriers in the same DWDM channel to increase bandwidth or to optimize performance for longer distances. And what we are seeing right now is that 800 gig pluggable coherent optics will come probably end of this year. And I mean, there are two things. Either we increase the baud rate, keep the modulation format, and get higher speeds, or we keep the, let's say, baud rate, use a better modulation format and extend distance. So there's always a drawback of, let's say, higher data rates or longer distance with these pluggables. But it's all going to higher speeds and longer distance overall. One thing which is quite important is these 100 gig QSFP28 coherent modules coming to market now. Byron already talked about it. So that will bring 100 gigabit DWDM embedded optics for almost all switches, routers, OLTs, DSLAMs that are supporting QSFP28 optics and allow customers to build that type of networks without transponders or muxponders in the access. Yeah, or even in the core, but metro core. So looking at 400 gig, there are 2 or 3 challenges, I would say. One is the bandwidth of the modulated signal of a 400 gig signal is around 60, what did we say here, 63 gigahertz, 65 gigahertz. Many old days DWDM networks are using actually DWDM filters that have not been designed for this passband. So upgrading an existing ROADM network with 400 gig requires a couple of things. One thing is to make sure that the ROADMs or the filters, the dispersion compensation modules are actually good to take these signals and to transport these signals without seeing penalties. If 400 gig doesn't pass through in some applications, 200 gig 16 QAM might be an alternative. So it's a smaller bandwidth, which is almost in line with the 100 gig QPSK signals and allows you to run 200 gigabit over your network. Yeah, the next thing is the power levels. I already mentioned 400 gig ZR and ZR Plus had pretty low output powers, so like -6 to -13 dBm. So those require, let's say, either preamplifiers before you enter a ROADM network or a network that has been designed to take these signals. With the high power optics, we are more or less solving that problem. So we have a couple of customers that are running 400 gig ZR high power over their existing ROADM network without any problems. So I think these are manageable challenges if you know what you're doing. OSNR, of course, is another thing, but these are all things that are, let's say, doable. Our experience so far is in point-to-point networks, 400 gig ZR and ZR Plus, is already there. So we are deploying point-to-point networks day by day, more or less. Internet exchanges, data center interconnect, and all these applications are working very well. The acceptance of ZR and ZR Plus optics in switches and routers is there with most of the, let's say, big vendors that are providing 400 gig equipment. And amplifiers can solve it if 400 gig ZR Plus optics with high power are not supported yet. In existing ROADM networks, there are the challenges that I already mentioned. So we have the first project already installed. There are greenfield deployments happening right now. So the service providers that are just starting to build their networks, have one advantage. They can just take on this new technology and build a network that is optimized for IPoDWDM with 400 gigabit coherent optics in their host systems. The adoption of IP over DWDM in existing networks is a bit slower than expected, and the main reason is that the switch and router vendors are lacking a bit behind with support of these high power optics. So as I said earlier, there's support in the firmware required in order to run these optics embedded in a switch or router, and that's not really there yet. So we are doing lots of trials and qualifications with system vendors as well as with service providers and enterprise customers to test what's possible and where are the limitations. So, practical example, let's say for a point-to-point DCI link. It's an open line DWDM system connecting two sites over dark fiber and a coherent pluggable in a switch. And one drawback in the past with IP over DWDM was always it's hard to manage. But with these, let's say, optics today, they provide all the optical parameters that are required to judge if an optical link is actually performing well or not. So in the past, we just saw transmit and receive power, and that's it. With today's optics, we can actually see prefect bit error rate, we can see OSNR from most host systems, and that gives us a very, very good, let's say, measure of the quality of the link. And we could even get early warnings when the layer 1 isn't performing well. If it goes even worse, layer 2 or layer 3 will be affected as well. So we can basically monitor the fiber, and we can monitor the in and outgoing signal on the open line system, as well as in the switch, which means we have end-to-end monitoring for every service through our DWDM network. So that's pretty easy and not complex at all, and brings DWDM basically to every customer, even if they don't have vast experience with that technology. This is an example of a CLI output from a Juniper router. So here you also see that we get all the information about the optical layer, about the operations mode. They can run in 400 gig mode, 300 gig mode, 200 gig mode, 100 gig mode. So the lower the data rate, the better the performance over distance. And there's also statistics available about prefect bit error rate, OSNR power levels over time. So you get a very, very good visibility of the performance of your DWDM signal. The same thing can be done on a ROADM network these days. So there's not really a need to have all these complex transponder-based solutions. If we run it in a ROADM network, we can actually simulate 400 gig services, 100 gig services with different type of transceivers. So here it's a high power 400 gig transceiver according to OpenZR+. And we can simulate the service end to end through an ROADM network based on OSNR values from the network, distances and power levels. So you know from your planning tool already if a service is feasible to be deployed or not. And once it's deployed, you also get on a ROADM network all the information from the endpoint of the service terminating at the ingress and egress of the network. So you get a full service visibility in an open ROADM network or in an old ROADM network with these embedded optics. So that's my last slide. Thanks for your attention, and
thank you very much.
Any questions?
Do we have any questions? Not a question.
It's me again.
Hello again.
Graham from the internet. So you were saying that the management in the coherent optics is giving you the same stuff that we've had previously from the transponder systems? Is it complete feature parity, or is it like most of the stuff?
I mean, yeah, it depends what transponders you worked with before, but I mean, the most important parameters are typically input, output power, OSNR, prefect bit error rate, and these kind of things. I think here, I forgot his name, Flex Optics guy will go a little bit deeper into the details of the monitoring capabilities of the 400 gig optics, so he has way more details about that. I just wanted to point out that these, let's say, base layer 1 parameters are available in, I think, every core router and switch that I'm aware of right now.
Okay, so that was going to be my second question, is the capability is dependent, as you said, on the firmware, and what is the availability across the different vendors right now? Is it kind of everybody's there, or are there people lagging?
I mean, I can just name, let's say, the vendors that we worked with so far. It's Juniper, Nokia, Cisco, Arista, Huawei. To my knowledge, all of them are presenting all these parameters in their host systems right now. And I expect that to be, let's say, common across the board, because otherwise carriers and cloud providers, data center operators, even enterprises wouldn't accept this technology if they don't have the right, let's say, visibility of the optical parameters in the network. It's essential to run an optical network to have these performance parameters.
Yeah, no, I agree completely. I mean, we have some challenges with some of the fiber quality in the country at the moment, and we are finding that we have to have that visibility, otherwise we can't fix issues.
And I mean, just in case that the host system do not have all these parameters, I mean, transponders are still there. So we are just saying, use this technology where you can, but if a transponder or a muxponder is adding value because you're increasing, let's say, the capacity of an optical channel through your network, yeah, use a muxponder. If you need a demarcation in order to hand over to a long-haul carrier, use a transponder. And with the open ROADM features of the next generation of QSFP-DDs, where we will also get layer 1 encryption, I doubt that the router and switch vendors will implement firmware support for encryption very soon. So if you want encrypted layer 1 services, I mean, that might be also a feature for a transponder, adding value at the same time as having a demarcation.
Hi, Andrew Dolgan on Nokia.
Sorry, could you say that
Hi,
again?
Andrew Dolgan on Nokia. I would ask you to be careful about what you state about what vendors do. On our routers, we support this. We've been supporting the 400 gigahertz for quite some time. We do interoperate. You showed Juniper. We do interop with them. We manage this end-to-end. We do have encryption at full rates on any levels in hardware. So let's kind of stick to what we do and not pass what other vendors do. I'm not going to go and defend other routing vendors. If they hear, they would come and probably defend themselves. But from Nokia perspective, this is a definitely good technology. We do support it. It's being deployed. The quality of the fiber is a problem. Yes. I'm not a layer 1 guy. I'm an IP guy, but I know the quality of the fiber is a problem, especially for a distance. But it's definitely good technology.
Yeah, I mean, I would totally agree. I mean, the physical, let's say, boundaries are the same for all vendors. So we can't overcome high losses and poor, let's say, fiber network qualities with technology, at least not just to a certain extent. And yeah.
Got a couple more questions, if you don't mind.
Yeah,
we're making use of some Alienwave services from other carriers. Is that functionally equivalent to what you were referring to as the open line system?
Yes, absolutely. I mean, that's the whole idea of having an open line system, that it supports third-party waves through the network. And I mean, there are different approaches to that. Some vendors, I mean, have it implemented as, let's say, open from day one. Some vendors have their license models. Some vendors have design tools for open, let's say, alien wave services. Some vendors make it a bit more complicated. But I think the trend to request alien waves through a third-party ROADM-based network or even a multi-vendor ROADM network is definitely increasing with this technology right now that the pluggables bring to market.
Yeah, we currently have IP device, a standalone box doing a transponder, and then it goes off into the network. And so this theoretically means you can put a pluggable into the IP routing device and eliminate the transponder if it's not serving a purpose.
Yeah.
And then the last question I had was we use a lot of this kind of stuff in our access aggregation, so at fairly short distances. And you mentioned dispersion control, and I haven't been able to find good information on this. Can this kind of stuff work without dispersion control or dispersion compensation when you're talking about like 10 to 40 kilometer ranges? Where does dispersion compensation become important?
So the dispersion compensation with coherent modulator optics is basically taken care of in the coherent modulation. So the ZR optics are specified to run up to 120 kilometer distance with regards to dispersion. The ZR plus optics go up to like 450 kilometers. And that's actually also the reach that you can expect from a 400 gig ZR plus optic with amplified links. So 450 kilometer might sound like a dispersion limitation, but when you are going 450 kilometers in an amplified network, you're already hitting the OSNR limit anyway. So 450 kilometer right now, I think, is the ZR plus limitation. But with lower data rates, you can go even further. And when the 800 gig optics will come to market, they will come with 800 gig 16 QAM modulation, or alternative with a 400 gig QPSK modulation. So that means with 400 gig QPSK, you can actually take a 400 gig signal to like 1,000 or maybe 2,000 kilometers because the OSNR is just way better. The drawback with that is that the 400 gig modulated signal will require even wider band. So instead of like taking 65 gigahertz, it will probably take 125 gigahertz or something like that because the baud rate is just doubling, and with that, the spectral will double as well. I mean, another way to optimize OSNR for 400 gig is Raman amplification, but with bad fiber networks, Raman, I mean, doesn't really help a lot. It can help to lower OSNR, but it cannot help to overcome high fiber losses.
Cool.
Yeah, thank you.
Thank you for all those questions. Perfectly on time for 10:30.
Yeah,
Thank you, Matthias.
So, well, thank you.
Thanks. Next up is Thomas Weibel from Flex Optics. He's going to talk about coherent optics, how they work. Scary